23, and we need to multiply that by 1.25, or you can divide it by 0.8, right? So 23 times 1.25 is going to be what? It's going to be 6? 29. 6, so it's going to be 29. So 150 minus 29 is going to equal to what? 121? What does that tell me? That tells me his what? No. That doesn't tell me his AA grade. What does that tell me? That big long formula, I mean, this short, is the formula for what? It's the alveolar oxygen. So this is his alveolar partial pressure of oxygen in the alveolus. Okay? The AA gradient is the difference between this number and the measured number. So the measured number is what? The arterial number. What's his arterial oxygen? Okay, so 121 minus 95 is equal to what? 26? Is that normal? Well, remember, you gotta compensate for the age. So what is the formula again? It's 99 plus what? 10. 10? The whole thing over 4?
Yes, it's normal.
Okay, so that's like what? 10 over 4, 26, 27, something like that. So his AA gradient is normal. Okay? So maybe he doesn't have pneumonia. Maybe his infection is urinary tract infection or something. Okay. Next question. Next problem. So a 55-year-old man is admitted with weakness, anorexia, weight loss, and polyuria. So they give us vitals: 120, blood pressure is 122/76, temperature is 101, respiratory rate is 22, pulse is 105, and these are his labs. Sodium is 135, potassium is 5.4, chloride is 101, bicarbonate is 12, pH is 7.32, PCO2 is 24, and the PO2 is 104. Is there anything that anybody didn't get? Huh? 105. Okay, so the first thing that we have to ask ourselves in the acid-base approach to this patient is what? Huh? All right, is there an alkalemia or an acidemia? So which one is present? Okay, so there's an acidemia. So what is the minimum diagnosis? Again, what are you going to look at? You're going to look at the PCO2, and you're going to look at the serum bicarb. So what's the minimum diagnosis that explains the acidemia? Say it again. Metabolic acidosis. Everybody see that? He has to have a metabolic acidosis. It cannot be he can't have a primary respiratory acidosis that explains it, because the bicarb is because the PCO2 is low. It doesn't explain it. Right? So you have to at least have a metabolic acidosis. Next thing we calculate is the NIF. Okay, so how do we calculate that? It's sodium minus so it's sodium minus the sum of the chloride and the bicarbonate. So it's 135 minus 113. Everybody see that? If you don't see it, make sure that you raise your hand, okay? Because you have to understand this. It's 135 minus 113, which is 22. So the anion gap is 22. All right? So what that means that the person has what kind of metabolic acidosis? Got an anion gap metabolic acidosis. Okay? And we talked about the differential diagnosis of an anion gap acidosis. The next step is we have to calculate the delta gap. Okay? So again, what we're saying is you take the measured anion gap and you subtract the normal anion gap from it, and the difference is the delta gap. So what's the delta gap in this case? 10. What do we do with the 10? You use the 10 to calculate the starting bicarbonate. Okay? So if the bicarbonate in this patient that's measured is 12, and we add 10 to it, then we get a starting bicarbonate of 22, which is near normal. Okay? Normal is 24. So now we can, so far all we have is a single metabolic, it's a single disturbance, a single acid-base disturbance. So far we have a metabolic acidosis anion gap type. Now what we want to do is we want to see, this is different from the last one when we already knew at this stage that we had a mixed acid-base disturbance. Okay? So what we want to do now is we want to see if the compensation is appropriate. All right, so we're dealing with a metabolic acidosis. So if you look at the table of compensatory responses, okay, what you'll see is that the formula for metabolic acidosis for compensation, there's 3 different formulas that are listed there. You can use whichever one you want. But the compensation, or I guess the Winter's formula is the one on top. PCO2 should be equal to 1.5 times the bicarbonate plus 8 plus or minus 2. I think that's the Winter's formula. So the PCO2 should be equal to 1.5 times the bicarbonate plus 8 plus or minus 2. So if we take the bicarbonate of 12, bicarbonate of 12, and we multiply that by 1.5, that gives us 18, plus 8 is 26 plus or minus 2. So it's anywhere from 24 to 28. It's 1.5 times 12. Because 12 is the bicarbonate in this patient, the measured bicarbonate in this patient. Plus 8 plus or minus 2. And you see that the expected compensation is going to be somewhere in the range of 24 to 28. Okay? And this is close to that. Okay? So you can conclude that the compensation is appropriate. So we're dealing with somebody who has a metabolic acidosis, a primary metabolic acidosis, with respiratory compensation. Yes.
So the Winter's formula, if you're looking at the starting bicarb and it falls within the range of what a normal bicarb should be, and it assumes that compensation is appropriate, you have to do that in the formula.
Say that again.
So if you calculate your starting bicarb, like you did, and it's a 22, the 22 falls within the normal range of what a bicarb should
Yeah.
be. So we can
I see what you're saying. You're talking about the starting bicarb, as opposed to the one that you're seeing on the blood gas.
Right.
Yeah, they do the same thing. They're both doing the same thing.
Oh, okay.
All right. This is just checking compensation. If you've calculated that the starting bicarb is in the appropriate range, and then calculating compensation is redundant. So this person has an anion gap metabolic acidosis, and we ask ourselves, we go through the differential diagnosis. Differential diagnosis includes lactic acidosis, ketoacidosis, renal failure, or ingestion. So that could be salicylates, formaldehyde, ethylene glycol, or methanol. What do you think is most likely in this patient? He's got an isolated anion gap metabolic acidosis. Let me summarize it in a little bit different way. Just knowing what we know. Okay. Okay, we would say he's a 55-year-old man with fever, weight loss, and polyuria. Okay, who presents now with a non-anion gap metabolic acidosis. Huh? Yeah, it looks like ketoacidosis, right? Because if all you knew was that he's polyuria and weight loss, what would you think about? You think about uncontrolled diabetes, right? So that makes sense. What about the fever? He had probably something is going on that has precipitated this DKA. Maybe he's got pneumonia, maybe he's got a UTI, maybe some other infection that has precipitated the diabetic ketoacidosis. What about his sodium of 135? Let's assume that a normal, let's say for the lab, normal is 140 to 144. Tell me why his sodium is wrong. What do you think? Why? Polyuria? Okay, well, when you have polyuria, do all people with polyuria have hyponatremia? There is a right answer to this question. You know what it is? Why his serum sodium is low? No, you need to think about some of the stuff that we talk about these days. Huh? No. What is this? He is. So why? What are some of the things that are associated with? Remember when we talked about hyponatremia? Remember the differential diagnosis? You can look in your book. Look at it. What's the differential diagnosis? Why does this patient have hyponatremia? No. Huh? No. Diabetes insipidus. Diabetes insipidus, is that associated with hyponatremia? That's the opposite, right? No, that's not why he has it. Say it again. Aldosterone? No. Look at
Did you already say no SIADH?
No to SIADH. SIADH is associated with hyponatremia, but this is an SIADH. No renal failure either.
Hypothyroidism?
Nope. Hold on a second. Look at page 60. Yes! It's pseudo-hyponatremia. So they didn't give us his glucose. They didn't give us the glucose, okay? But whenever the glucose goes up, remember that the serum sodium is going to fall 1.6 for every 100. Okay, let's assume that this patient had a starting sodium of, well, we don't know what the starting sodium was, okay? Here's what we know. We know that so let's assume that it was 140, okay? Let's assume the starting serum sodium was 140, okay? And let's assume that, well, we're not assuming it, we're told that the serum sodium is 135 now, right? What's the serum glucose? I should ask this on the test. What's the serum glucose?
You said normal 140.
Yeah, let's assume normal is 140. So estimate what the guy's serum glucose is.
400.
Okay, so you know that from 100, you assume what the normal glucose is 100. All right, for every 100 above that, this falls 1.6. So it's gone down 5. So you divide 5 by 1.6, right? Is that what you do? What is that going? 3 times? So it's got to be around 400. Yeah. Okay? Everybody see that? So this is pseudo hyponatremia, pseudo hyponatremia. And that's important to realize that. Okay? Let's talk about the potassium. Why is his potassium? Why is his potassium high? So you do know. Well, listen. Potassium can be high for what are the 3 different things that can influence potassium? Okay, so it could be cell lysis. So in other words, it could be coming from the cells, or it could be a problem with excretion with the kidneys, or it could be a problem with intake, right? What's going on in DKA? Yes. So how does that cause? What does that cause? Yeah, it shifts. It causes as the body tries to buffer the pH, protons are going to go into the cell, into the intracellular space. Potassium is coming out. So everything that we talked about is happening in this guy, right? He has pseudo-hyponatremia. He's got hyperkalemia because of shifts related to across the cell membranes related to acid base. This is like a textbook, right? Case. This is perfect. All right. Let's calculate his AA gradient. Okay. Let's assume he's also on room air. So what's his AA gradient? So let's see. We're gonna first calculate his alveolar oxygen, right? So it's going to be 150 minus 24 times 1.25. So 1.25 times 24 is going to be 30. So 150 minus 30 is 120. So his alveolar oxygen is 120. Alveolar oxygen is 120. His measured oxygen is what? 104. This is his T arterial. Okay, so the difference is the AA gradient. 120 minus 104, which is equal to 16. Everybody see that? Now, what's his calculated AA gradient? So it's 55 plus 10 divided by 4. So this is near normal too. Okay? Everybody see that? I gave you a couple of formulas. The first one was the age plus 10, that whole thing divided by 4, or age divided by 4, that whole thing plus 4. Either one of those is going to give the right answer. Yeah. Hyponatremia? 100 is normal. 100 is let's say normal. We use that as an estimation of what's normal. Okay. So what we say is, for the serum group, for every 100 elevation in the serum glucose above 100, so this is the floor, above 100, right? The serum sodium will go down by 1.6. Okay? So if you know that 1.6 goes into 5 3 times, okay? Then you start at 100, all right? And you say, you count 1, 2, 3, so 200, 300, 400. You're adding 100 times 3, but it's not this 100 that you're dealing with, it's for every 100 above 100. Any questions about anything that we talked about there? Yeah.
When you said in step 8, I think, you said it was a primary metabolic acidosis with respiratory compensation. Is the only reason you said that was because you noticed that the PCO2 was well below normal?
I said, you don't know that you're dealing with appropriate compensation until you plug in the formula for compensation, okay? Or until you, depending on the acid-base disturbance that you're talking about, you might know when you calculate the starting bicarbonate. But you can sometimes know sooner that you're not dealing with a simple acid-base disturbance. So, for example, one of the things that you'll notice if you look at page 67, figure 322, is that in all of those panels, A, B, C, and D, the CO2 and the bicarbonate are moving in the same direction, right? If they're moving in opposite directions, then you know, before you do anything else, that you must be dealing with a mixed acid-base disorder. Because look, all of the simple acid-base disorders, those two things move in the same direction. Okay? Now, just because they're moving in the same direction, it does not follow that you're dealing with a simple acid-base disorder. It means that it might be a simple acid-base disorder. Okay? It might be a simple acid-base disorder. You still have to work through the steps in the progression to make sure that it is a simple acid-base disorder. If they're moving in the same direction, all it tells you is it might be a simple acid-base disorder. If they're moving in different directions, it tells you that it cannot be a simple acid-base disorder. Okay? Everybody see that? Yeah, I don't use the base excess. So I'm not really familiar. I don't use that too much in the calculations. But do you know how to do that?
I wasn't sure if you use that just to simplify. If they're both moving in the same direction, and it's outside the...
I don't know the answer to that. I don't know. But, what I would encourage everybody to do, if you haven't done it yet, is work through all of the problems. They might talk about that on the University of Connecticut tutorial. It is a tutorial. You're supposed to work through it yourself. They may talk about the base, because there's different approaches to acid base. This is only one. So it doesn't matter which approach you use. You could use a completely different approach than the one we're talking about in class. Just as long as you use one that works, and you use it and apply it appropriately. Let's do one more, and then we'll stop. Okay?
Oh, Dr. Paola. Yeah. The last guy, he was in DKA and had a pseudohyponatremia.
Yeah.
Okay, thank you.
Okay, 33-year-old woman brought to the emergency department 5 hours after ingesting pills in suicide attempt. On exam, she is stuporous. Blood pressure is 115/70. Pulse is 116/116. Respiratory rate 24. Temperature 99. And these are her labs. Sodium is 140. Potassium 4.1. Chloride 106. Bicarbonate is 10. And on the blood gas, the pH is 7.54. PCO2 is 12. And CO2 is 106. Okay, so is she acidemic or alkalemic? Okay, so she's alkalemic with a pH of 7.54. And then what is the minimum diagnosis that must be present in order to explain respiratory alkalosis? If you look at the PCO2 is down 12, it's at 40. If you look at the bicarbonate is low. So that would not explain the alkalemia. We would expect an acidemia. Okay? Yeah, and so you should be thinking about it if you're dealing with somebody that has one of those mixed disorders. So you're dealing with something that looks like it might be mixed, although you don't necessarily know that yet. You calculate the anion gap. What's the anion gap? 24 is right. So this person has an anion gap acidosis in addition to a respiratory alkalosis, right? So double checking yourself. Does salicylate cause an anion gap acidosis? One of the 4 ingestions that's associated with an anion gap acidosis. Now we work our way backwards. We got to calculate the delta anion gap, and the delta anion gap is going to be you take the measured anion gap and you subtract the normal anion gap from it. So 24 minus 12, and that gives you 12. And we use that then to calculate the starting bicarb. So we take the measured bicarb, which is 10, and we add 12 to that, and we get 22, which is near normal. It suggests that there's no other metabolic problem present besides the metabolic acidosis, the anion gap metabolic acidosis. So this is somebody that has a primary respiratory alkalosis and a primary metabolic anion gap metabolic acidosis. You don't have to calculate compensation in people who have mixed disorders. So we found two disturbances here. And your hypothesis about that this is a salicylate overdose, does that make sense? Given the acetate disturbance and the clinical history? Makes sense? Let's calculate her oxygen gradient. So if she's breathing room air, what's her alveolar oxygen? What's her alveolar oxygen? Yeah. Let's see, 150 minus 15 is 135. So her alveolar oxygen is 135, and her measured oxygen is 106. So her AA gradient is 29. She's 33, so is that okay? So if we take, let's see, age plus 10, so she's 33 plus 10 is 43 divided by 4 is 11. It's a little high. right? Would you say it was 29? So her AA gradient is a little bit high. So if you had to bet, what do you think is going on with her? Good guess. That's a good bet. She's super. She probably did ask for it. Okay? And you should be able to figure that out if you're given a choice about what might have happened. Could it have been well, you know it's not hypoventilation, right? Because you have to see the bicarbonate there. It's not that. The AA gradient basically tells me that there's a problem with diffusion at the alveolar pulmonary capillary interface. You also know that she's not in a room where the FiO2 is less than 21%, right? Because that does not give you a problem with the gradient. All right. Huh? Say that again?
She shifted left from the disassociation curve to pH.
Okay. So, would that be a different process than what we're talking about, though? All right. So, you guys feel somewhat comfortable with this stuff?
Oh, so with the rules for compensation, are those things that you want us to go through and glean from this website and memorize?
You don't have to memorize those rules. You can always look them up. And for the testing purposes, I'll give you the formulas for compensation. You don't have to memorize. So they'll say, formula for metabolic compensation for metabolic acidosis. And you can always look that up. I never remember them anyway. But you have to know how to apply it. And so in order to know how to apply it, you have to be able to recognize these things. I can't tell you strongly enough. Make sure you go through that tutorial, otherwise you're doing yourself a disservice. Right? So in the time that we have left, does anybody want to have any questions about anything that we've talked about? I think the test is next week, right? Monday or something? So does anybody have anything that they want to ask? Any concepts that they want to go over or they're not sure about?
Oh, that's the old.
Yeah.
When you get a bicarb on a CMP or BMP, can you presume that it's the same as you would from a blood gas? The bicarb will change.
They're usually Any questions about any of the things that we've covered? So on the test, it's going to be pulmonary and renal, right? Yes. Yeah.
Can you go over really quickly what the starting bicarb is telling you?
What the starting bicarb what?
It's telling you, I'm assuming that it's telling you that there's compensation or there's not compensation.
Yeah, it's telling you. It's telling you that whether there is or is not another process, another primary process besides the, let's say, the anion gap you've already identified. So, for example, when we talked about the examples that we talked about today, the first one was the 99-year-old man, right?
Yes.
So when we talked about him, and we calculated the starting BIFAR as being 33. All right, so that told us that there had to be a primary metabolic alkalosis besides the anion gap metabolic acidosis that we had already found. Because otherwise, how would the starting bicarbonate be 33? That's the normal bicarbonate is 24. So this is 33, so that's consistent with an underlying metabolic alkalosis. So it told us that there was another primary process. Yeah.
So in that case, the first thing we said was that he had respiratory alkalosis.
Right.
Then we calculated that he had an anion gap acidosis.
He had abnormal anion gap. And then we calculate the starting BIFAR.
And we found a third disturbance.
That's right. He had 3 disturbances.
So at that point, when we have more than one disturbance, is that the point where we can say we don't calculate for compensation?
Once you have one, you don't calculate for compensation. With mixed anion gap acidosis, with mixed acid-base disturbances, you don't have to calculate for compensation.
So if they're both alkalotic, you have to, but if one is acidotic and one is alkalotic, you don't have to.
No. If they have mixed, could be anything. Mixed means that they have more than one process. They have of the 4 primary processes that we talked about: respiratory acidosis, respiratory alkalosis, metabolic acidosis, metabolic alkalosis. If they're mixed, you don't have to compensate. I guess if somebody has a respiratory if somebody has, let's say, metabolic acidosis and metabolic alkalosis. No, because it screws everything up. Once they have a mixed disorder, I don't think any of the compensation formulas are good. So once you've determined that they have a mixed acid-base disorder, then you don't do the compensation. See, think about it this way. The reason you do the compensation formula is to see whether there is a mixed acid-base disorder. Because if the compensation is not appropriate, it means that there's another primary disturbance. So once you've established the presence of all the disturbances, of multiple disturbances, then it doesn't make any sense to calculate the compensation. We did it with the first one because I wanted to illustrate how you use those formulas, and I wanted to illustrate what I wanted. I wanted to illustrate something, so we applied it with that case. But if you don't apply it with mixed and I think they make that pretty clear. They do a good job at explaining that in the Connecticut thing. So, and their approach is a little bit different, but you might like that approach a little bit better. All right. Well, listen, good luck. If anybody has any questions, you can email me over the weekend or whatever.
Thank you.